So there is a close link between integrals, or finding antiderivatives, and area before we start talking about what the relationship is, because there's a very important relationship between integrals and area. But before we start talking about that relationship, I want to spend some time talking about the idea of area and how we can approximate the area under a curve, because there will be an important relationship between that area under the curve and the integral of the function whose curve you're finding the area under. So I've got these notes here. I guess you could print them out if you wanted to. I'm just going to go through them with you. This is part one. There is a second part before we start talking about the relationship between integrals and area. So the focus today is, how can I find, what are the methods of finding area or approximating the area under the graph of some function? So you can see, like in that first diagram there, we've got a curve, and it's not so easy to come up with a formula for that shaded region under the curve bound by the x-axis. So that light blue shaded region, we're going to try and approximate regions that look like that, but there's no formula because it's not a geometric shape. We've got a function that's curved. And so the area, that blue region, is not, for instance, a square. It's not a rectangle or a triangle or a geometric shape that we can easily find the area of. So we're going to try and approximate that area. And the most common, or one way of approximating that area, is by using rectangles and then summing the area of the individual rectangles. Okay, so if you look in the second picture there, that area has been broken down into four rectangles, four purple rectangles, which would approximate that area under the curve. But you can see in the diagram or the picture that it's not a really good approximation. Above each rectangle, you've got this area that we have not accounted for. Okay, so that approximation, which is often called a Riemann approximation, that approximation would underestimate the actual area. Okay, because the area, if I sum up the areas of the purple rectangles, they are definitely going to be less than the actual area. So that would be an underestimate of the actual area. So this summing of the areas of the rectangles is often referred to as a Riemann sum. Okay, so that second diagram there with the four rectangles, choosing four rectangles is a random number. Just so happens that I chose four. But we could try to approximate that area using any number of rectangles. And it would turn out that the more rectangles we use, the skinnier those rectangles are going to get. They'll have a smaller width. And the more rectangles we use, if you look at the third diagram there on page 2, you can see that all those tiny areas above the rectangles get smaller and smaller if we use more rectangles. So the more rectangles we use to approximate the area, the better the approximation is going to be. And our approximation will be closer to the actual area of the under the curve. The problem is we need to determine how to position or where to put these rectangles. Okay, so Riemann approximations, often called rectangular approximations. If you hear them, those are interchangeable. So I can call these rectangular approximations. We're going to be using rectangles to approximate the area, but there's going to be three different methods we use, and what determines the method is where we're going to position these rectangles. Okay, so the common conventions are, or the common practices or processes are, or methods, a left Riemann approximation method, a right Riemann approximation method, and a midpoint approximation method. So what the left, right, and midpoint refer to is where we're fixing the rectangles, or each one of the rectangles. So if we look at the left Riemann approximation, or the LRAM for short, what we do there is we're going to position the top left-hand corner of each rectangle on the graph. So you can see from that first picture there, each rectangle's top left-hand corner is on the graph. Now, a right Riemann approximation would place the top right-hand corner on the graph. So you can see in the second picture there, each rectangle has its top right-hand corner on the graph, and that is what forms the height of each rectangle. Now, in the first picture with LRAM, definitely an under approximation. But with the RRAM, we have an over approximation because our heights extend above the graph when we draw the rectangles. You can see we've got these four pieces of the rectangles that are above our function. So that would be an overestimate. The third method is not to use the top left corner or right top corner, but to choose the midpoint of each rectangle to lie on the curve, and that would be an MRAM approximation, or a midpoint Riemann approximation. So we've got four rectangles in that picture, and it's the middle, the center of each rectangle that lies on the curve. So it's the center of each rectangle that will form the height of each rectangle. Any questions so far? Okay, partitions and subdivisions. So in all those pictures there, so first of all, I guess a partition or subdivision refers to the number of rectangles we're using to divide the X interval. Okay, so if you use a partition with 4 rectangles, you could use a partition with 10 rectangles. The width of each rectangle will change, or the subdivision will change. Now there's 2 types of partitions you can use. One is a uniform partition. All that means is all the rectangles will have the same width. That is the more common one, and it's the one that we'll use most of the time, if not all of the time. But there's no rule that says that all these rectangles have to have the same width. We could use a mixture of wider rectangles and skinnier rectangles. That would be fine as well. That would be referred to as a non-uniform partition. So the rectangles do not have the same width. Either one of them is a valid way of subdividing the X interval that we're using, but we're going to use the uniform partition because it's a lot easier. The calculations are a lot more straightforward. So an example. So we're given the graph of some function here, and we're being asked, part A, use the left Riemann approximation method, or the left rectangular approximation method, to determine approximation for the shaded area there from x equals 2 to x equals 6 using 4 equal subintervals. So if we're using LRAM, okay, first of all, the subintervals are going to look like this. So if I extend these, you can see where the 4 rectangles come into place. But now it's the top left corner of each of these rectangles is going to form the height. So I'm going to have a rectangle like that. Then this would go up to here and form the height of the next rectangle. Then I move to the third rectangle and I would get something like this. And the fourth rectangle would look something like that. Okay, and now the area, the approximation, I'll shade in the highlighted yellow here, is this. So we got 2 rectangles, 3 rectangles, 4 rectangles, right? Once you get the rectangles drawn, this is not rocket science, right? It's just about deciding what the height is going to be. So the height, again, for LRAM is dictated by the top left corner of each rectangle. And now all you do is count the squares. So we've got 3 here, 7, 6, and 4. So the area is approximately equal to 20. Now, not sure if that's totally going to be an overestimate or underestimate. The first rectangle underestimates the actual area, and the last 3 kind of give us a little extra, so they're overestimating the area. But in total, I'm not sure whether those 3 extra pieces would cancel out the underestimated rectangle. In any case, the area there is 20. Now we can do the exact same thing for RRAM. And then I'll have to erase that and do RRAM. But the point here is just so that you understand how this works. So let's go through, I'll go through that process. I'll erase this. Now I need to use RRAM to approximate the area from 2 to 6. So again, I get these strips here that I'm going to turn into rectangles. Okay. Now the first rectangle's height is going to be dictated by the top right-hand corner. The next rectangle, top right-hand corner. Third rectangle, top right-hand corner. Fourth rectangle, top right-hand corner. And if I shade that in, or I could shade that in, I get that first rectangle there. Having trouble coloring here today. There. And there. So, to approximate that area, all we do is, it's nice that the grid is there. But if the grid wasn't there, I'd just be multiplying the width by the height. of each rectangle. So first one, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, and 4. So 21. Okay. That's how you would use a right rectangular approximation or a right Riemann approximation. Any questions? Okay, we can do this again. Here's another example. Use LRAM to determine approximation for the area between that function and the x-axis from -2 to 4. Okay, but this time you're being asked to use 3 equal subintervals. So 3 equal subintervals. I'm going to have this kind of situation here. Whoops, not there, but there. And so if I'm using LRAM, the height of the first rectangle is going to be what? Anybody? Here's the height right here, it's 0. Right? The second rectangle will be like this. And the third rectangle, if I'm using LRAM, would be like that. And so my area, so your area is going to be the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3. The first one is 0. The next one is 4 times 2. And the last one is 6 times 2. So that's approximately equal to 8 plus 12, which is 20. That's for LRAM. Now if I erase that and go through the exact same process, except now I'm going to use the top right-hand corner of each rectangle that I form as the height. Then I will have some of the first rectangle that looks like this. My second rectangle drawn like so. And the third one like that. And you can see in each case the top right hand corner of each rectangle forms the height, or is where I get my height from. So in this case I would have that the area is equal to 2 times 4 for the first rectangle plus 2 times 6 for the second rectangle plus 2 times 4 for the last rectangle, which is 8 plus 12 plus 8, which gives me 28. Now my guess would be for that, just by visually looking at it, that that's probably an overestimate of the area. The next example, now we're given an equation. We have a function, but now we actually have an expression for the curve. So that curve there I've drawn is y is equal to 2 to the x. Okay. Approximate the area under the graph from -3 to 3, part A, using a right rectangular approximation with 3 equal subintervals. And then state if it's an overestimate or an underestimate. So we're going from -3, which is here, to 3, which is there, using 3 equal subintervals. So I need to divide that up, the distance from -3 to 3 into 3 subintervals, and then use RRAM. So my first rectangle, or the last rectangle, I should say, will look like this. The second rectangle, like so. And the third rectangle, something like that. Okay, and now I need to find the area. So the area is approximately going to be equal to rectangle 1 plus rectangle 2 plus rectangle 3. So the width of each rectangle is 2 units. Okay, so the area of rectangle 1 would be my width, which is 2, times the height, which is f at -1. Okay, this height here would be f at -1. Plus the area of rectangle 2 would be a width of 2 times the height, which is the value of the function at 1. And my third rectangle would be the width 2 times the height, which is f at 3. So this would be 2 times 2 to the -1 plus 2 times 2 to the 1 plus 2 times 2 cubed, right? This is f at -1, this is f at 1, that's f at 3. Those are just the y values of where my dots are on my diagram there. So this is 2 to the -1 is a half, so that's just 1 plus 4 plus 2 cubed is 8 times 2 is 16, so I get an answer of 21. It's an overestimate. Now, why is it an overestimate? Because of these areas here that are not under the curve, they're way above the curve. But based on the way I chose my rectangles, that's as good as it gets using a partition of 3 rectangles. So just in case it's not clear, this height is f at 3, this height is f at 1, and I'm sure I can't squeeze it in there, there's not enough room, but the height of the first rectangle is f at -1. Part B, now we're doing the same thing, only using LRAM. So -3 to 3, using 3 equal subintervals, means that again the widths are going to be 2. The width of each rectangle is 2, except now the height is formed by the left top corner of each rectangle. So like so, like this, and this the first one is very difficult to draw, but like that. So if I'm writing an expression now for the area is going to approximately be equal to the area of rectangle 1 plus 2 plus 3. So rectangle 1 is a width of 2 times f at negative 3 The area of rectangle 2 is our width of 2 times the height. The height of the second rectangle is f at 1. And the last rectangle has a width of 2 and a height given by f at, this should be negative 1, my bad here. The second rectangle has a height dictated by f at negative 1, and the third one is f at 1. So that's 2 times 2 to the negative 3 plus 2 times 2 to the negative 1 plus 2 times 2 to the power of 1. So f at negative 3 is this, f at negative 1 is that, f at 1 is just 2 to the 1. So this is 2 times 1 over 8 plus 2 times a half plus 2 times 2, which is a quarter, plus 1 plus 4. Which is 5 1/4 or 5.25. Overestimate or underestimate? Definitely an underestimate. Any questions on that? Okay, now the third one is do the same thing, but now use a midpoint rectangular approximation. So, again, from negative 3 to 3, the width of each rectangle. So we're partitioning the distance from negative 3 to 3 into 6 equal subintervals. My bad. Oh my God, this calculation is going to be brutal. So 6. And on top of that, we need to use the midpoint of each one of those. So, what that means is, if I go to the end there, that means that in my last strip, the rectangle is going to look something like that. In the second last strip, so I'm taking the midpoint of each subinterval. So the midpoint of the second last one would look like so, which gives me a rectangle that looks like that. And then this one here, like so. Okay. And then it becomes messy, but you get the idea. So we're using the midpoint of each one of those strips or rectangles. So what we need to do is, this is going to be a little more lengthy. The width now, in this case, because we're using 6 subintervals, we take the distance from negative 3 to 3, 3 subtract negative 3 and divide it by 6, which means our width this time is going to be 1. So the area of 6 rectangles now we have to add up. So rectangle 1 has a width of 1 times a height of whatever the y value is at negative 2.5. The second rectangle has a width of 1 times the height, which would be f at negative 1.5. The third rectangle has a width of 1 times a height of f at negative 0.5. Plus, so that's the first three, plus the fourth rectangle, so I've done 1, 2, 3, a width of 1 times a height of f at 0.5. Fifth rectangle has a width of 1 times a height of f at 1.5 plus 1 times f at 2.5 for the final rectangle. And now we need to evaluate all those. So let me just use a calculator here. So the first one is 0.17678 plus 0.3535 plus 0.5 plus, oh, hold on, that one's wrong. 0.707 plus 1.4142 plus 2.828 plus 5.6569. And then we can sum those up. $11.136. Now you're not asked if that's an overestimate or an underestimate. That is, the more rectangles we use, the more difficult it is to determine whether the approximation is an overestimate or an underestimate. But you can see when you compare the picture from part C that your approximation is definitely going to be better in part C than it will be in part A and B. Now, we can't do an exact comparison with the actual area because we don't know the actual area yet. However, in a short while, not today, but we're going to see how that area is related to the integral. So, any questions on how to approximate an area using an LRAM, an RRAM, or a midpoint rectangular approximation? So that's how you would do it given a function. Now, quite often on AP exams, you'll be given something like this, which is just a table of values for a function. And you're going to be asked to approximate the area under the graph using different approximation methods, using RRAM, LRAM, or the midpoint. So, let's go through this. You can see, so it's best if you can visualize this, okay? You can see that the x values are 3 units apart, right? So that difference there is 3, that difference is 3, and that difference is 3. So we're being asked in part A to use RRAM with 3 equal subintervals to approximate the area. Now, it's not necessary. You could draw a little sketch to help you out, but it's not really necessary. And it's faster if you can do it without drawing the sketch. Just visualizing that you have 3 equal subintervals split up from 1 to 10. Okay, and now if I'm using RRAM, okay, I'm going to have 3 rectangles. So my area is going to be approximately rectangle 1 plus rectangle 2 plus rectangle 3. Now, what is rectangle 1, the area of rectangle 1? Well, they all have a width of 3, so it's going to be 3 times. But now, if I'm looking at this chart and saying, well, what's rectangle 1? Well, rectangle 1 has a left height of 6 and a right hand height of 8. So I want to use the 6 there. That forms the height of the first rectangle. Oh, sorry, that's RRAM. That's should be 8 for RRAM. Right? This is the left and this is the right for the first rectangle. So I want to use, for RRAM, I want to use the right hand height, which is 8. Then I go to the second rectangle. So I'm going to erase this and this. My second rectangle, I would be using these data points. Okay, 8 would be the left and 3 would be the right. So the area of the second rectangle would be 3, which is the width, times 3, which is my height. Then I go to what I would consider the third rectangle. And I'm using these data points 3 and 5. This would be left, this would be right. So I have a width of 3 times a height of 5. And so I get 24 plus 9 plus 15, which is 48. Now, we'll do LRAM. Same thing, 3 equal subintervals. So for the first rectangle, those are the data points I'm using, the 6 and the 8. However, 6 now is left, 8 is right. So again, I can write, I'm summing up the areas of these rectangles. So the first one is going to be a width of 3, except now the height is not 8. For LRAM, the height would be 6. Okay. When I go to the second rectangle, I'm using these data points, 8 and 3. Maybe I'll just erase that so it's not confusing. I'm using for rectangle 2 these data points, 8 and 3. And now this is my left height, this is my right height. So I'm going to take my width of the rectangle, which is 3, and multiply it by the left-hand height, which is 8. And then finally, for the last one, I'm going to get a width of 3 times a height of 3. Okay, so again, for the third rectangle, I'm using these data points. This would be the left, this would be the right. And so I would choose 3 there for the left. Then I just multiply these out. 18 plus 24 plus 9. What's that, 51? Okay, now, any questions on that? So that's how you would do it using a table of values. If the function's given to you in a table of values form. Here's another example. Just given more data this time. And you can see that again, the partition is uniform, so each x value is 0.5 apart. Okay, so we've got 0.5 for all of these. And we want to approximate the area under the graph of that function, even though it's not a graph, we're using a table, using LRAM. Now, it doesn't tell us whether we should use what type of partition we should use. However, I'm just going to use a partition. So 1, 2, 3, 4, 5, 6, 7, or 6 rectangles. So we're going to use 6 rectangles. Each with a width of 0.5. So if I'm doing LRAM, when I write this out, I'm going to get, now the width of every single one of these 6 rectangles is a half. So why don't I just pull out that 1/2 outside. Okay, that's the height of every single one of the rectangles, and then just write down what the heights are. So for the first one, it's going to be 2 plus 4 plus 6 plus 7 plus 4 plus 1. So that's 1/2 times 24, I believe, which is 12. Now, for our RAM, we'll use 6 rectangles again. Okay, the width of them is still 0.5, except now, notice that for the LRAM, I used all these here. The RRAM is going to be different. The RRAM is going to be 4 plus 6 plus 7 plus 4 plus 1 plus 5. So what have I done there? I've used these data points. And I just add those up, multiply by a half. 27, I think. So what's that, 13 and a half? So you can see that no matter how many rectangles, if we had the same idea there, when we're doing LRAM, you're going to include every data point except the last one. And when you're doing RRAM, you're going to include every data point or every f of x value except the first one. Any questions on that before we do MRAM? Because MRAM for this one is a bit different. So part C says approximate the area using MRAM. So what you are not to do is to take the values in the chart and start making up your own data. Okay, so what do I mean by that? What I mean is, let me just erase this. What I mean by that is I don't come here and I say that the midpoint in between here is 0.25 and then take the average of 4 and 2 and write down 3 to give me some other data point. No, that is not what we do here. Okay? Because we're being asked to do a midpoint with the given data, we have no choice but to do this kind of thing. We're going to use this from 0 to 1 as the first partition. Then we're going to use 1 to 2 as the last partition. And then 2 to 3 as the third partition. And the reason we do that is because these data points here that I'm highlighting would be the midpoint of those three partitions. Okay, 1/2, the 0.5 is in the middle of 0 and 1, 1.5 is in the middle of 1 and 2, and 2.5 is in the middle of 2 and 3. Okay, so the way that table is laid out for you lends itself well to MRAM with 3 partitions. Okay, keep in mind when you're doing these approximations given a table, you can't just make up data from the take the data and change it to fit the type of approximation you're doing. So in this case, the area is going to be, now again, the width of all 3 rectangles is just 1. Okay, so W is equal to 1 here. So I can take that outside, okay, and just multiply by the height at each midpoint. So the height at the first midpoint is 4, the height at the second midpoint is 7, and the height at the third midpoint is 1. Okay, it's these values here, 4, 7, and 1. And then I just add those up and multiply by 1, and I get 12. Any questions on that? Okay, let's start this next example. So here we're given a polynomial, x cubed minus 5x squared plus 6x plus 5, and we're being asked to approximate the area between that graph and the x-axis from 0 to 4. And part A says using a right rectangular approximation with 4 equal subintervals. So from 0 to 4 with 4 equal subintervals, my width is going to be 4 minus 0 divided by 4, which is just 1. So here you can see what the partition is going to be. Now with RRAM, how is that going to look? That would be the first rectangle, okay? The second rectangle would look something like this. The third one like so. And the fourth one way up there, somewhere around there. So we're going to sum up the areas of those rectangles, and that will approximate the area. So R1, R2, R3, R4. Our area is approximately equal to. The width is 1 for all of these things, right? For each one of the 4 rectangles, the width is 1. So I can just take the 1 outside. The height of the first rectangle is F at 1. The height of the second rectangle would be F at 2. The height of the third rectangle would be F at 3. And the height of the fourth rectangle would be F at 4. Now, I don't have a numerical answer for that, and I don't want to waste another 2 or 3 minutes doing that. So let's just go on to part B. Okay, F at 1, how do I get that? I just sub 1 into the original function. F at 2, sub 2 into the original function, etc., and then add them up. So I'll do that later, and I'll write the answer in here. Now, LRAM, rather than me erasing that and doing all this again, this time the left-hand side, the top left-hand corner is going to form the height. So this expression is going to be slightly different. It's going to be a width of 1 for every rectangle, but now the heights are going to be F at 0 plus F at 1 plus F at 2 plus F at 3. Okay, so not like that. That's L. That was RRAM. LRAM is going to look. So here's 1. Here's 3 is going to look like this.